Welcome back, everybody, to the second today. So now we have Lisanne Taams from the Radboud University in Nijmegen, who's going to be talking to us about torsion sheaves on stacky curve or how to compute a motor. So Lisanne, when you're ready, please take it away.
Hey, yeah, thank you. Yeah, exactly. I'm going to be talking about torsion sheaves on stacky curves, and then hopefully we're going to compute the motive of the moduli stack of torsion sheaves on the stacky curve. For me, the goal of this talk is mostly to sort of bring motives a bit to a wider audience and convince everyone that they're not so scary. So maybe to start, who has heard about motives? Yeah, that's some people. Who is scared of motives? That's even more than the people who have heard of motives. So who knows what a motive is? So no one. So I think maybe we're just all scared of the unknown. So yeah, so maybe I'll start with just sort of making motives a bit less unknown and hopefully less scary. So let me start with a question. Has everyone ever computed an invariant of some space? Who has computed an invariant? Well, can someone give me an example of an invariant they computed? Sheaf cohomology, sure. Someone else? Chow group, nice one. One more? Someone over there computed something? Maybe this is all we've ever computed as a group. I think there was L-adic cohomology, right? Yeah. Oh no. No, we'll do L-adic cohomology. So right. So okay, I mean this one's a little bit special maybe, but somehow invariants follow all kind of the same pattern. You start with some sort of category of your favorite spaces, maybe schemes or something. And then there is some functor, which is probably cohomology, going to some sort of abelian category, maybe vector spaces or graded vector spaces or whatever. But really, to me, cohomology is just some functor from some category of spaces which you care about to something abelian. But satisfying a bunch of nice properties, right? It should satisfy lots of nice properties. And then motives are just the best one. So there's motives somehow should be a functor from your favorite things. So maybe we'll do just stacks because that's our favorite things. And then we should go to some category, which we'll just call the category of motives. And this is what motives are. And then why are motives so good? Because every other sort of invariant will factor through this one. Which means that if you can understand this functor and this functor, then you just can compute all the invariants you want. This is great, except that this category doesn't exist. So there's a fix, and this fix is that we do have a functor, but instead of having an abelian category here, we have a triangulated category, whatever that means. So instead of exact sequences, we have triangles, but don't think about it too hard. Just pretend there's a nice, perfect abelian category that computes all the invariants. And that's what motives are. Okay, so maybe that's a bit vague, but we can make this like super concrete by doing examples. Yeah, so what is it? Like if you have a triangle, then it somehow should correspond to exact sequences, or maybe long exact sequences. So yeah, you can make that work. But we're gonna sort of do this in a context where it's sort of gonna be obvious what you should be doing here. I mean, these functors here are sort of in the literature. Like I've never actually tried to apply one of these functors, but you can do it. It has definitely been done. For me, I just do this part and I'm happy. Yeah, so oh yeah, I should say that this triangulated category, it definitely has a sum, but it also has a tensor product. Then maybe let's see some examples of motives. We can take, for example, the motive of a point, and it will turn out that this is the identity for the tensor product. So maybe we'll call this one Q or something. Then in general, here's some other motives. You can take the motive of a curve. That's a motive. You can take the motive of maybe just X, where X is a smooth projective variety. There's a very special motive, which is some sort of twist of this guy, which I'll say something a little bit more about. But in general, this is sort of what we're going to do. We're just going to take some nice things, take their motive and say, oh, this is a motive. We can do plus, we can do tensor product. And now we have a whole bunch of motives. And then what we do in practice is we take something more complicated. It's like some moduli stack, for example. We take M, and then we try to rewrite it in terms of these nice things. And then the point is, for these nice things, we sort of know how to go to our favorite invariant. And we also know how our favorite invariant goes with plus and tensor product. So if we can rewrite our motive in terms of these nice things, then we can definitely compute all the invariants we want. Yeah, so I'll write down some, yeah, for example, M satisfies that M of M cross Y is M of X tensor M of Y. Yeah, and the same for plus. So you can see that sort of the operations in this category have very geometric interpretation. Tensor product is like product. I'm not sure, like half of the properties are requirements and the other half of the properties are theorems, but it depends on your construction, which are which. So. Yeah, so somehow we should pick coefficients for a category. I'm going to do Q coefficients. That's sort of all I'm saying here, actually. But you can see from this that if you tensor with the motive of a point, then that's like taking the motive of this product, so it doesn't do anything, right? So the motive of the point is just like tensor with Q, doesn't do anything because we were already over Q. Yes, sorry. Yeah, you can do this over. Yeah, so this is sort of Q coefficients. So it's more, it's the Q over here. So if you commute cohomology groups, you get Q vector spaces. Maybe you would get abelian groups and you should work with Z, but we'll just work with Q. It's a little bit easier. You can definitely work with the integers, but then some of the results I state will not be true. Right. So maybe let me give you some theorems or maybe formal properties that help us compute motives in terms of these nice things. Here's like a very fancy one, but somehow not so fancy. So let's say we have a complex of vector bundles, a two-term complex of vector bundles, just a linear map. On our favorite stack X. Then we can take the motive of the quotient stack. And this will not do anything. So what's the point here? You can think of, say, V0 is 0, and this is just a one homotopy, saying that if you take a vector bundle over something, doesn't change the motive. You can always contract along A1s. And this is the fancy version. So I'm also saying that you can contract along some BGAs as well. And then you can also do it combined at the same time. But yeah, this is just A1 homotopy in the most fancy version. Then there is guys in triangles. So say you have some smooth open closed pair. So some open with a smooth complement. Then I get a triangle. Then I get a distinguished triangle. Here you need to tensor with this guy over here, with the codimension of V. Okay, this is a triangle. I think if you were scared of motives, you will not be happy with a triangle. So I will upgrade this a little bit. So this says, say I have a triangle such that M1 and M3 are pure. So what does pure mean? Pure means that you only use these guys over here in your motive. So your motive is like a sum and tensor products of smooth projective guys and these ones. Yeah, I'll say a little bit more about that one later. This is sort of, it's a Lefschetz motive or the Tate motive, depending on who you ask, I think. No, it's like somehow, it's like a double shift in the different senses that you can shift.
So you're going up.
So this one, yeah. So this is apply this shift, which is the same as tensoring with that motive. Yeah. C is the codimension of V. So it's sort of, yeah. Okay, so if we have a triangle, I don't like triangles. The outer ones are pure, so they're just made up of guys over there. Then the triangle splits. So what does it mean for a triangle to split? I mean, it means that the middle one is just M1 plus M3. So we upgrade all our triangles into direct sums, as long as we can ensure this purity. So maybe let's do like a super quick example of this one. So let's do P1. And then our closed open pair is going to be A1 and a point. Point is definitely smooth. So this says that the motive of A1 goes to the motive of P1, goes to the motive of the point, which we're calling Q, twisted by the codimension. Codimension is 1. Plus, we remember A1 homotopy. So M of A1 by the first one is just also Q. So these are pure. So this one is actually Q plus Q1. And if you want, you should take this as a definition of Q1. That's in a lot of sources, that is the definition of Q1. And then Qi is just the tensor power of Q1. So Q1 is the thing that sits inside of P1. That's not the point. So you sort of want to think of this as sort of being a line sitting in something compact. So the line, of course, contracts. but this is a line that cannot contract because it's stuck. That's how I think about it. So this somehow is a non-contractible line. Okay. So now we've actually already computed the motive. See if we can upgrade that. Let's do Pn while we're at it, right? So who has a guess for what the motive of Pn should be? Yeah. Yeah, right. And how do we know that? Well, you can take Pn. We can take a point inside of it. Is that the best way to do it? Yeah, exactly. Click Pn -1, and then what is the complement? Yeah, great. This is the close one, it's the open one. And then right, and you just do this again. And then you apply induction, right? And then you'll see that every time you do this, you add a Q n. So this will give you that the motive of Pn is Q up to. Sorry. Oh, sorry. Yeah. And maybe if you've ever computed any of the other invariants of projective space, now you know why this computes all of them at the same time. So this explains why they're all the same, right? So somehow it's a bit magical that all these different invariants output the same thing. Okay, now I'm going to give a very complicated theorem, which we will use in a bit. Okay. Let x to y be small, surjective, and generically G torsion. So what does this mean? Well, first of all, generically a G torsor. This means that it's almost a G torsor for a finite group. And that there is some part where it's not a G torsor. And in fact, it's allowed to have positive dimensional fibers there. But small says that the locus where it's not a G torsor has high enough codimension. And I will not say what high enough is, but somehow the part where this is not a G torsor has high codimension. And like the more it's not a G torsor, the higher the codimension should be. Yes, that's a perfect example, which will show up in the talk. Somehow. Right, so say you have this situation, then we can take the motive of x. And then it turns out that the smallness condition is exactly enough to ensure that this G action, which acts on like an open part of x, actually lifts to the motive. Any finite group. And it turns out that if you take the invariants of this motive, which I will not define what the invariants are, but in the examples, it will be very clear what the invariants are. Then this is the motive of the base. So somehow, if this was actually a G torsor, this wouldn't be so surprising, but it says that you can sort of mess around with it a little bit and works on level of motives. Yeah. I've got it. I guess so. Right, yeah. Right. Yeah, if the point is high enough codimension. Yeah, so small means that, okay, so generically this map is finite. You can go to the locus where it's not finite, and you can look at what the dimension of the fibers is there. And then the codimension of this locus should be at least twice the dimension of the fiber. So maybe blow up doesn't work. No, the dimension is too big. Yeah. Okay, good. Yeah. No, so yeah, you really, really, really high codimension of this locus. And I guess the blow up is not high enough. Yeah. Right. Okay. Okay. So now we know. Yeah. 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 I think this is a theorem in like highest generality. If you want it, like, no, it's still a conjecture that it might exist somehow. Okay. Okay. So maybe with integral coefficients, yeah. Yeah. Yeah.
That already sort of becomes.
No, it's very non-obvious. Yeah. So actually, if you restrict to like smaller subcategories, then it does work. So for example, if you only have pure motifs, then you have the category of Chow motifs, which is an abelian category. No? Oh, okay. Well, almost. You can do some stuff there, right?
Yeah.
Yeah. Still not good enough. Okay. Yeah. Okay, so well, let's ignore it.
Already in the decomposition.
Yeah.
Yeah. I mean, this should be the some example.
Yeah.
That should be a structure.
But let's avoid like all the parts of the category that are complicated. Try to stay in here. That's how to be a little bit less scared. Okay, so this is motifs. I'm going to say something about torsion sheaves and stacky curves, and then we'll try to compute a more complicated motif than this. So if you ever open like a book on motifs, they will only ever compute this motif, and then you're like, good luck, right? So after this, you'll be almost an expert. Okay. Okay, let me give just the definition of a stacky curve. Who knows what a stacky curve is? Like almost no one, yeah. So we know all these very complicated moduli stacks, but we don't know anything about curves. So, okay. Stacky curve is one-dimensional. So one-dimensional DM stack over fields should be an arbitrary field. Don't worry, you can pretend that this is complex numbers. And then maybe, like depending on what you want the curve to be, you can add adjectives here, right? So you can add like irreducible or geometrically irreducible. You could add proper. What should curves be? Anyone have a favorite adjective for curves? Yeah, for curves, proper is the same as projective. And also for DM stacks, proper is the same as projective. Yes, thank you. Yeah. So actually, I'm just saying that there's some open substack, which is actually a scheme, non-empty open substack. Yeah, let's add smooth actually. Good idea. Yeah, in general, I will just add all the adjectives you want. Because this is a definition. Yeah. So actually, these things are very concrete. So let me give you an example first. Let's say you take A1, you can let mu E act on it by rotations. So it's not proper, but it's an example of a stacky curve. If you want to make it proper, you can maybe glue another one in. You sort of glue them like you would glue projective space, right? And then you get like projective space with mu e stabilizer and another stabilizer. And it's actually a theorem that all stacky curves can sort of Zariski locally be glued together from these quotient curves. So actually you really just use these guys as your local model. You glue them together, you get stacky curves. You can do Zariski locally. So étal locally, they are just curves even, right? You can unquotient this. But Zariski locally, they are these quotients. Then you definitely have to have smooth for that. No, so you need to put other smooth curves here. Oh, sorry, yeah. So yeah, so Zariski locally, they look like C mod G, or this is a curve and this is a finite group.
Any curve, or can you kind of ask it?
Oh yeah, sorry, yeah, if you want to put smooth here, you should put smooth there. These sort of inherent the same properties, right? Okay, then these guys have good moduli spaces, and they're also coarse moduli spaces. And I think it's sort of kind of clear what happens, right? This will just be P1, because the good moduli space of this one is just A1 again. It's twisted around. So yeah, these are stacky curves. So and maybe as I don't know if I'll use this, but I have some notation that if you have a stacky curve, I'll write it like curly, and then there's always a map to its good moduli space. Yeah. Okay, so stacky curves very easy. Now let's do coherent sheaves and stacky curves. So the definition is just it's a coherent sheaf on a stack, so that's fine. But they have ranks and degrees and stuff. So so the rank of a coherent sheaf is defined to be the rank of the push forward. And for locally free sheaves, this will give the correct definition. So this is what we'll take as a definition. And then there's a bit of a problem that degrees are not, like the degree is not precisely the correct invariant. I will have something a little bit more complicated. I will have a twisted degree di for every stacky point. So maybe let's assume there's only one stacky point from now on for convenience. So let's make this A1. Move that guy. Okay, so a stacky curve with one stacky point. These are the degrees of the push forwards of F tensor with O. Right, so I take the line bundle that corresponds to the divisor of the stacky point. I write it like this for some reason, and then you can take the degree after twisting. And in general, these numbers are not the same. So P is the unique stacky point. So okay. So you can already see that, say you have, let's do only torsion sheaves from now on. So torsion sheaves are rank 0 sheaves. This is a curve that's correct. Say you have some torsion sheaves that's supported away from the stacky point, then this twisting doesn't do anything. So for torsion sheaves away from the stacky point, all the twisted degrees are the same. But it's going to be the torsion sheaves supported at the stacky point that will do something special. Yeah, so let me explain what torsion sheaves. Okay, you know what torsion sheaves look away from the stacky point, right? Just torsion sheaves. But let me do torsion sheaves at the stacky point. So say I have some point in my curve, which is a stacky point. Then I take a chart, which is some curve, maybe something else. And in fact, I can make this group even the stabilizer group. It's always a cyclic group. Discover. And then a torsion sheaf of this point, we can lift the point up to some new point here. And torsion sheaves on this point are the same as torsion sheaves on this point. So then maybe tilde, so this is the same as torsion sheaves. We tilde. And then we can remember some equivariant theory. So this is mu E equivariant torsion sheaves on, maybe add. So at Q, so Q is, okay, no, it can't go up anymore. So there's U and U has the point Q. So we can do the mu equivariant torsion sheaves with Q. Then we'll pass to some linear algebra or commutative algebra. And what is this? This is graded Q modules. It should be torsion, so probably finite. Right, and then we apply graded Nakayama's lemma. And this is the same as finite dimensional G mod easy graded Q module vector spaces plus a grade 1 map. So torsion, so this map is going to be nilpotent. Right, so this map is the action of the uniformizer, and then this is sort of commutative algebra nonsense. But modules over here or vector spaces over there with some action of the uniformizer. Okay, and then who has ever seen quivers before? Okay, everyone, right? Or almost everyone. This is a quiver representation, right? This is a quiver representation of the cyclic quiver. So there's some points go in a circle. And there's E points, there's E maps. You can put your graded vector space on top of this diagram by putting each grade of your vector space on the correct thing. Your grade 1 map will be all these small little maps. And then we ask that it's nilpotent. So this shows that torsion sheaves and stacky curves are represent nilpotent cyclic quiver representations. Okay, so that's kind of strange. And then these degrees, suddenly we know what they are. These degrees are the dimensions of these vector spaces. So D0 is the dimension of the 0th one. The 0 comes from this grade. Which you can figure out if you just follow all these arrows over here very carefully. Maybe you'll just believe it. And actually, you kind of know a theorem like this already for curves, maybe. It says that if you want a torsion sheaf on a point in a curve, it's the same as a representation of this quiver, a nilpotent representation of this quiver for the people that have seen. Okay. Now we have 10 more minutes to compute the motive. Any questions about torsion sheaves? Yeah, so I mean, you can take them all, but once you know E of them in a row, you won't know all the others. This is sort of the point. So for a vector bundle, they will not go, they will just sort of keep going up. But there's a pattern, and the pattern repeats every E times. Okay. Okay, so now we're going to try to compute the motive of the stack of rank 0 coherent sheaves with specified twisted degrees over some stacky curve, which will have one stacky point for convenience. Maybe I should say this is smooth Artin stack. It has a good moduli space. So I'm gonna keep it a secret what it is. Okay, so now we're gonna, does everyone remember the small map stuff? Because we're gonna write down a small map. So I'm gonna define some sort of filtered stack. So this twiddle 0D, and this is gonna be torsion sheaves, or this is gonna be chains of torsion sheaves. Let me do some notation. So I want to write my D as a sum of the one vector and then some remainder. This will be convenient. So the one vector is just one in every spot multiplied by A, so A in every spot. And then I want a remainder. Remainder should be as small as possible, but positive. And I want chains of torsion sheaves like this, such that T0 sits in the original thing, and the kernel of all of these guys sits in 1. So the kernel should have degrees, twisted degrees 1 everywhere. So you can see that we can do this exactly 8 times before we run out of 1s. And then TA sits in this one. Somehow we'll filter all our torsion sheaves. And then this guy naturally has a map to the thing we started with by just taking the first one. And I claim this is a small map and it's an SA torsor. The smallness business is a lot of dimension estimates, but they work out. And to see that it's generically an SA torsor, you can sort of think of the torsion sheaves where the support is just a different point. So at least for this part, it's a different points and then some stacky business. And then you can order these a different points, and this will give you a filtration like this. If you order them differently, then this filtration will just be ordered differently. So generically, this really is just an SA torsor. So we get that the M of this guy is the M of the twiddle invariant part. Maybe it doesn't look like this helped, but this one is actually much easier to compute, because it also has another map. By taking all the pieces take this one 8 times. And it turns out that this is one of these generalized vector bundle maps, which A1 homotopy applies to. Because to go from here to here, you sort of have to give some extensions. So this is going to be some sort of extension bundle. So it's going to roughly look like this. So the fibers are going to look like this. and actually it satisfies the condition. So the motive of this is the same as the motive of that. So this is somehow really the SA quotient of something very pretty. We have 5 more minutes. So I now need to sort of tell you what the motive of this one is and what the motive of this one is. Or maybe first let me tell you how to interpret these invariants now. It's very clear in the example. So we can just we're wondering about this. It turns out now that we've transformed everything, it's very clear how SA acts geometrically already. So this is and then the symmetric product. Right, so we sort of see that this is kind of a natural thing. Let's do this one first because it's kind of easy. So remember, B was as small as possible. So B has a 0 in it. If B were all zeros, then there wouldn't be anything there. And if not all of them are 0, then we know that we are supported at the stacky point. So away from the stacky point, the twisted degrees are always all the same. So either you're all zeros or there's some difference. So we know that we're exactly in this quiver representation picture. So actually, this is the stack nilpotent. But even better, because there is a 0 in the B, this nilpotent condition is just empty. So one of the vector spaces is 0, so going in a loop always brings you to 0. So this is just some not some sort of GL. It's really, we just have to pick a bunch of maps and quotient out by GLNs. And you just have to be convinced that these motives are kind of easy to compute. So that one's not so bad. And then let's do the one with all ones. Yeah, you're right. Yeah, these are the matrices between the vector spaces. These are the base geometry. So this one's kind of fun because you can have a torsion sheaf not on a stacky point, and it can degenerate into it can move into the stacky point, and it has many options of what it can do there. So you can see that the stack is not separated at all, but it is as complete. So what I will do for this one is I will give you an open-closed pair. Namely, I will take the coarse space, and then over here I will have some sort of representation space. So what do I do? So let's say, what I want to say here. Right, so what are these? These are quiver representations. Such that this one is 1, and maybe not necessarily, such that at least one of these maps is a 0. And I'm not saying anything about the first one. So this is sort of a subset of the quiver representations. And these I just put in here, and these will have a description like this. Again, that's doable. And then the point is that how do you put the curve in here? Well, away from the stacky point, it's sort of clear if you have a point, you take the skyscraper sheaf and put it in there. But then what if you have a torsion sheaf at the point P? Well, it's a torsion sheaf. It's rank 1 by assumption, so this map has to be 0. And then you sort of extend this loop. So you have V here. V is just K actually, but you put V here. And you put V sort of everywhere. And you make all of these maps the identity. Somehow you unwind this loop. You just plug in that one. And this embeds C into this, and the complement is this big representation space, where again you have a very concrete description. And then you have that the motive of this one is, or this is not quite right. There's a GM stabilizer hiding. Should be this, right? Because this has a global BGM. This one also has a global BGM stabilizer. But okay, yeah. So if you have a quiver here, you just unwind it to get a quiver there. This is an embedding, and you apply once more the Gaussian sequence. Then you've computed the motive of this one, you plug it back in that one, and you do everything recursively, and then you've computed. Okay, thank you.
Any questions for Lisanne?
Yeah.
About
Yeah, I can say something about that. So sort of the idea is that as your stacky curve, you just take A1 mod mu E. And then if you pass through these equivalences to the commutative algebra, you can see that a torsion sheaf on this is just a cyclic quiver representation without the word nilpotent there. So because now we allow it to go outside, it sort of removes the nilpotent part. And then exactly this map code tilde, this one, this is the gradient nilpotent. Yeah, this is the gradient Grothendieck-Springer resolution. And so, for example, when E is 1, so this is just A1, it is actually the honest. And maybe D should really be A times all ones for it to actually be the Grothendieck-Springer resolution. This is the Grothendieck-Springer resolution. Yeah, for GLA, I guess. Yeah.
It's not graded in the sense of graded.
So it is. So if you sort of push everything through and start writing down everything, you get graded Lie algebras. And I have some formulas that are written down here, but would have to spend like a lot of time writing them down. But you can ask me. Yeah.
Grading on GLA.
Yeah, exactly. Yeah. Yeah. But actually, it even works when D is a little bit unbalanced, but then you have to be a bit careful about what all the matrices are, but you get a picture for any D.
Yeah, so I didn't explain this picture of cone of zero. It's quiver that looks like.
Yeah.
And I got where the cyclic one came from, but where the
Oh, sorry, no, so I mean that you want the zeros on some of the maps. It wasn't it was just a bad picture. I just want some of the arrows, I forced them to be 0. Yeah. Just saying at least one of these arrows was 0. Yeah. Yeah. Yeah, so there, that's sort of, I don't ask for the first arrow to be 0. First arrow can be anything, but then maybe I even ask for it to be 1. Yeah, so sorry, I should ask for the first arrow to be 1. That forces a 0 somewhere else. Yeah, it's a 1, the first one, and then sort of to get the other ones, you have to put a 0 there.
0, 1.
Yeah, so underline is whenever I have a stack. So I think maybe it's ended up here somewhere. Yeah, so at one point I looked at the coarse space, and then you don't have to underline because there's 1 degree. Maybe that, or yeah, this one should be underlined. Sorry. So they should all be underlined, except when you're not working on a stack, and they don't. You can underline them, but they should always be underlined.
So this is all for a stack curve with a single stacking point. What if I have a look at a high dimensional variety with a single stacking point and still look at 0 dimensional sheaves?
Like it's a higher dimensional variety.
Yeah, but still looking at 0 dimensional torsion sheaves.
Yeah.
On the surface.
Yeah, I'm not sure actually what happens.
I mean, where do things start breaking down?
I've actually just not plugged it in. So actually this is sort of part of slightly bigger work where I do the full coherent sheaves, and there everything breaks down for surfaces because it's not smooth. But maybe just the 0 dimensional sheaves you could do on a surface.
Well, let's speak one more time.
Mhm.